Yes, students, good morning to all. This is P.K.Parrthipan, working as an assistant professor in the Department of Mechanical Engineering at Kamaraj College of Engineering and Technology. Today, we are going to discuss one of the important component in a kinematic analysis of a mechanism, and that component is Coriolis acceleration. So let us start our presentation. This is the overview of today's presentation. Let us start with coincident points. From that, we may come to know that what is meant by Coriolis component of acceleration. In that, we will broadly discuss about its definition. Then we can able to determine the magnitude of the Coriolis acceleration. Then we will discuss about the direction of Coriolis component and its significance. Let's start the topic. Coincident points. When a point on the link is sliding along another rotating link, then the point is known as coincident point. In other words, coincident point is the point on the slider such that the slider slides along another rotating link. The position of the coincident points varies as the slider moves in between its extremes position. Now I will show you this is the kinematic analysis of configuration diagram of a crank and slotted lever mechanism. This is link number 1, this is link number 2, this is slider which is considered as on link 3, this is another link 4, fifth link and another link 6. Here the link O1C, that is the link 4, is a longest link, and the link O2B, it is the link which is going to be act as a crank. So this link number 2 is going to be rotate. In that there is a slider. So this point has to be considered as a coincident point. So at this point it is forming a sliding motion along with a turning pair. Okay. Now the significance of coincident points. In general, the total acceleration of a point with respect to another point on the rigid link is the vector sum of radial and tangential acceleration. In our previous problems, we have able to find out the radial component and the tangential component only. Therefore, the total acceleration of any particular link is nothing but the summation of radial and its tangential component. This is only applicable the distance between the 2 points is likely to be fixed. Okay. Whenever a coincident point exists in a mechanism, that is, there will be a sliding point in one rotating pair or in a revolving pair. At that time, we have to find the total acceleration by considering very important component that is known as Coriolis acceleration. So that now the total acceleration is the vector sum of radial, tangential and Coriolis acceleration. Let us define what is mean by Coriolis component of acceleration. So as I told that it is going to be have a slider in a rotating pair. So that slider must have a coincident point with reference to that link. At that point, there will be a one tangential component. That tangential component of the slider with respect to the coincident point is known as the Coriolis component of acceleration. The Coriolis component of acceleration is always perpendicular to the link. And this corollary component of acceleration will always happen in various quick return mechanism like crank and slaughter lever mechanism, Whitworth quick return mechanism, and also in swelling joint mechanisms. Now let us calculate or derive the expression for the corollary component of acceleration. So let us consider this is one link. So this OA is a link and this link is having a slot. So this portion is, this entire structure is going to be a slot. In this slot, it is going to be have one slider. So this is the slider. If this link OA tends to rotate, means the slider will move along this slotted space, so that it is having a rotating pair along with the sliding motion, so that coincident point will exhibit. Let's continue. Let us consider a slotted link OA which has a slider B in its slot such that the slider block is free to slide in the slot. When this point O is considered to be a center and the link OA is now tends to rotate at a constant angular velocity of omega to its new position OA, so that this link is now going to rotate about an angle of d theta, so that the new position will be O dash A dash, and this change in displacement happen in the time dt. At that instant, the slider will move with a velocity v on this link OA and occupies a new position B. Okay. So now, as I told earlier, corollary component is a perpendicular is a perpendicular tangential component with respect to the coincident point on the slider, so that the distance B to B dash is nothing but corollary component of acceleration. So now we will derive an expression to find out this value B to B dash. Before that, we have to consider the motion transmit from B to B dash have done in 3 stages. Let us list out all these things. So B to B1 due to the rotation of link OA, then B1 to B2 due to outward velocity of V, and the third thing is B2 to B dash due to the acceleration perpendicular to the link OA, so that this distance B to B dash is nothing but corollary component of acceleration. So that from the geometry of the figure, this distance between this point B to B dash is equal to the distance C B dash, that is this distance is equal to this distance minus this distance. Now see, the arc B2 B dash is equal to arc C B dash minus arc C B2. The arc C B dash forms one triangle with respect to O. Let it will be in a form of a triangle. So this should be equal to OC into d theta. Similarly, the arc CB2 is equal to BB1. Here also it forms one triangle, and that magnitude of this arc BB1 is equal to OB into d theta. Now take this term d theta as a common one, so it will become OC minus OB into d theta. The value OC minus OB is equal to the distance between the point BC. So that I can rewrite this as BC d theta. And this BC is equal to B1 B2. So the arc B2 B dash is equal to now B1 B2 into d theta. Now I'm going to consider this as equation number 1. Now I'm going to take one assumption. That is not assumption, it is a concept from engineering mechanics. The displacement B1 in B2 is equal to the motion into time. So the motion is nothing but velocity of the slider, that is V into dt, and the angular displacement d theta by dt is equal to omega. From that we can rewrite d theta is equal to omega into dt. Now substitute this value. Instead of b1 and b2, I am going to substitute as v into dt, and instead of d theta I am going to substitute omega into dt. So that now the equation 1 becomes r b2 b dash is equal to v into d2, that is v into dt instead of v1 v2, and omega into dt instead of d theta. So that now the equation 1 can be written as v omega dt square. On the other hand, if you want to consider the acceleration of the system, we have to consider the equation of motion. We know that the one of the equation of motion is S is equal to ut plus 1 by 2 at square. Here the initial velocity u is equal to 0. So this term will get cancelled, or it may be equal to 0. So the displacement is nothing but the travel. The travel is arc b2 b dash, that is equal to 1 by 2 a dt square, that is change in time here. I'm going to consider this one as the acceleration, that is Coriolis component of acceleration. Now, for the small values of theta, the arc b1 b2 dash is equal to b1 b2. Now, I'm going to substitute this b1 b2 in here. That is arc b2 is equal to 1 by 2 at dt square, that is equation number 3. Now, we have to consider this equation with our equation number 2, so that v omega dt square is equal to 1 by 2 ac dt square. Dt square cancel on both the sides. This 2 will comes on this side. So now the Coriolis component ac is equal to 2 into v into omega. So that we have expressed the Coriolis component of acceleration in an equation form. That is AC is equal to 2 into V into omega, where V represents velocity of slider and omega represents angular velocity of that particular link. Now, let's move on to the very important thing. Here, in terms of a kinematic analysis, we have to concentrate on magnitude and also in terms of direction. Now we have calculated the magnitude of a Coriolis component as AC is equal to 2 into V into omega. Now the another important key factor is we have to identify the direction of this component. As I told earlier, the direction of the Coriolis component will always perpendicular to the link. Okay, that is obtained by rotating the velocity at an angle of 90 degree in the same direction of the angular speed. In our example, we have solved one diagram now, that will be in this case. Okay, here listen. Now the link OA is going to be rotate in a clockwise direction, so that the Coriolis component will always act perpendicular to this, and the magnitude is equal to 2 into V into omega. And V represents velocity of the slider, so that the slider will going to be tend to move in this direction. Similarly, these are the different possible directions for Coriolis component of acceleration based on two things. First one, direction of the crank and direction of the slider. So whatever may be the thing, Coriolis component is obtained by rotating the velocity at 90 degree about the same direction of omega. That is a concept. Very, very important thing. Why we need to calculate this Coriolis component of acceleration? What is the significance? Okay, let us discuss. So, if the Coriolis component of acceleration is neglected, means the link will have dynamic unbalance. That will the system does not undergo as a proper mechanism, which in turn leads to no slider motion with the rotating link. That is, no rotating link with the slider. This is practically impossible. So that we have to consider the Coriolis component of acceleration. So thank you for watching this. Thank you.